All right. So in the previous lectures, we talked about how we can have a small signal model for the transistor, and we looked at the application of that small signal model to separate the large signal, basically DC operating point, and small signal, changes that are not going to move the device away from that operating point by much. And then by separating these two from each other, we saw that the first part, the DC analysis, is a nonlinear analysis. You have a MOSFET, a BJT, a diode, whatever the nonlinear element is, that you would like to put in a certain operating region, right? So for example, the diode, you want it to be on, or the BJT, you want to keep it in active region, same thing with the MOSFET. Now, why do we want to keep them in the active region? The reason was that if they are in saturation or cutoff or triode regions, we saw that they do not respond to the changes at the input, right? So if the input signal is applied to the base and you look at the collector as the output, if the device is cut off, the current is zero, it's not really changing with the input. If the device is in saturation or triode regions, the output is essentially still independent of the input. So if you want to amplify a signal, if you want to just multiply the magnitude of a signal by some gain value, well, you cannot have that in saturation or cutoff regions. So we need to keep the device in active region, and that's the topic of biasing, which we will discuss next after we go through some basic amplifier stages. Once the device is in active region, you have those nonlinear sets of equations for both MOSFETs and BJTs that you use to figure out what is the DC current or DC voltages at different places in your circuit. Make sure the devices are in active region, to support the assumption you made at the beginning. And now you want to see what happens if a small signal comes in. And then those small signals could actually be a signal, for example, from a sensor or an antenna, or it could be a small change in environmental parameters. So if the temperature changes a little bit, usually the transistor parameters change as well. And you want to see how they affect the stability of the circuit or the operating point of the circuit. In most cases, the signal is actually a signal, right? It is coming from a source like an antenna, like a microphone, like a sensor. And you would like to amplify it because in a lot of cases, the source produces a very weak signal. It just produces a little bit of information, but you need to add a significant amount of power to that signal in order to use it on a driver, right? So the driver can be, or the actuator can be a display or let's say an electrical motor or whatever else. So the good thing was that by coming up with a small signal model, we essentially linearized the circuit. So instead of having to deal with all those nonlinear equations that we saw before, now you have a very simple linear equivalent for the transistors that you can use in your models, and now you're dealing with a linear circuit. And then, it's basically back to MSE 250, your circuit theory course. So we can actually look at all sorts of interesting parameters from the signal point of view now. So you can look at the input resistance of an amplifier stage or a circuit, which is essentially the resistor that if you put in place of that circuit, nobody else behind that will know. The source will not know that you took out the amplifier and put the resistor in its place if that resistor value is the same as the input resistance of the amplifier, or the gain of the amplifier, or the output resistance of the amplifier. We talked about all these parameters before, and you can go back and check the lecture notes for a reminder on these topics. But these are all small signal quantities, right? So we are calculating them, evaluating them based on the small signal model. The assumption is always that the device is not moved from its operating point by much. It stays in the operating region that you wanted it to, and it basically just responds to small changes at the input and output. For that reason, there's really no way of directly measuring, for example, an input resistance, because an input resistance is not physical. It's a concept, right? So you cannot put an ohmmeter to measure the input resistance or output resistance of a circuit. You have to come up with measurement techniques in order to give you those values, and you'll learn about those in the labs. Now, in this lecture, what we want to do is to look at 3 basic amplifier stages. You can make them with BJTs or MOSFETs. And once we learn these 3 stages, these are basically blocks, the building blocks for, I would say, 80 to 90% of amplifiers that you see here and there. There are, of course, other topologies that you can use, but in, I would say, 80 to 90% of situations, you can reduce a circuit that you see for the first time to a combination of these 3 basic stages that we will discuss today. So let's go back and have a look at a transistor. I'm going to talk about a BJT here. Again, as I mentioned before, this is a device that you can touch, you can buy. The discrete BJTs are everywhere, and you can play with them more easily than MOSFETs. MOSFETs are going to be very similar, as we will see, but I started the discussion with the BJT. So here is an NPN BJT. 3 terminals, collector, emitter, base, and these are the directions of currents, IB, IC, IE. And we saw that, effectively, you have 2 diodes here, and all the discussions regarding, these diodes need to be in certain operating regions. Base emitter has to be on, base collector has to be off. And once the device is in active region, we saw that you can model it with a nonlinear model based on this diagram. So this is your base, collector, and the emitter. This is your VBE, and the current here is, this is your IB, IE, and IC, and the current here is given by this nonlinear expression, ISE to the VBE over VT. Or if you know the beta of the device, you can also use beta IB because the device is in active region, right? So let me turn up the light. Okay, so this is as much as we get. Okay, so the question is that if I want to apply a signal here and get a corresponding change at the output, what can I do? So if I look at this model, it looks like that, because the variable source, the controlled source is here, I should use either the collector or the emitter as my output. These are the only 2 terminals that are affected by that controlled source, right? So the controlled current, the value that you're modifying by playing with IB or VBE, is going to affect the collector current or the emitter current only, right? So if you have a load that has to see some signal proportional to some input, you really shouldn't put it in the base terminal, right? There is nothing at the base terminal that is going to vary significantly if you have a signal applied to anywhere else in your circuit. So right off the bat, I see that for output, I can only use the collector or the emitter terminal, right? I do not use the base terminal to connect the load to it. The other way to look at it is that, remember, we want to add power to the signal. So let's say if you connect your source to the emitter and put the load at the base side, well, the emitter current is beta times, or beta plus 1 times larger than the base current. You're actually not going to be able to increase the power at the base side. Right away, you're losing so much on current. The voltage is going to be more or less the same. The difference is only VBE. So you will have significantly less power at the base end if you put your load there. So we do not use base as an output node. We cannot connect or we should not connect the load to the base. Now for the input node, well, think about where in this circuit, where in this model can you apply a signal such that the current changes. Well, if I look at this circuit, I can see that the current at the collector is IS e to the VBE over VT. So it's VBE that is setting the current. It is VBE that is my command. Therefore, I should either use the base or the emitter. If I change the signal, the voltage at either one of these two terminals, either the base voltage goes up or the emitter voltage goes up, I will have a corresponding change at the collector end, right? So obviously these two are potential input points. Collector is another possibility, right? So I can apply my voltage signal to the collector end. But at this point, I would like you to spend maybe a minute and think about why that wouldn't cause any change in my circuit. Why would it not be wise to connect an input signal to the collector terminal of a device in its active region? So maybe pause for a second, think about that, convince yourself that collector is not a good node for applying a signal to it. And then once you are convinced that it is not a good idea to use collector as the input and base at the output, you see that you will have limited combinations here. So you can apply your signal to the base and take the output from collector or emitter, or you can apply your signal to the emitter and take your output from collector, right? So if you look at these combinations, there are three possible topologies. So possible topologies, I'm going to write it, or possible combinations, let's call it, right? So I'm going to write input here. Input, this is node or terminal, so let's just call it input terminal. Now, what are the combinations? You can apply the signal to the base, okay? And if you apply the signal to the base, well, you have two terminals to get the output from. One is the collector, and another possibility is applying the signal to the base by taking the output from the emitter, right? So for the base as the input, you have two choices for the output. Another possibility is to apply the input to the emitter, and then since you're using that node for your input, then you cannot use it for the output. You only have one choice for the output, so that gives you collector. So apply the signal to the emitter of the device and take the output from the collector. And this is the only three possible scenarios that you can have for an input-output combination if you want to add power to the signal. For a MOSFET, the story is very, very similar. Again, you have gate, drain, and source, and you can go and show that, again, you have only three possibilities. You can apply the signal to the gate, take the output from either drain or source, or you can apply the signal to the source, take the output from the drain, and that's it. So only three possibilities. I'm going to stick with BJTs for now and go through the analysis and discussions with BJT first, and then we come back to the MOSFET stages or MOSFET equivalents afterwards. Okay, so because there is only three stages, we give them names, right? So for example, the stage here, so I'm going to call it the name or the stage, well, let's just call it the stage. So you're applying the signal to the base. I'm going to draw the transistor here. So let's say this is your input, and this is extremely simplified. We already know that, you need biasing and everything else around it. And taking the output from here. So this is VI is applied here, VO is taken here. So VI is between emitter or between ground and base. VO is between ground and collector. If you look at this configuration, emitter is basically connected to the middle point, right? So it's ground for both of them. So it's as if the emitter is the common node between the input and output. So I'll call this the common emitter stage. If it was a MOSFET, it would be called a common source stage. The second possibility that we see here is that the input is applied to the base, but the output is taken from the emitter. So this time I'm measuring the output from the emitter terminal. There is a ground potential somewhere that, because my collector is not party to this configuration, I can assume it is the collector one. So I'm applying the signal to the base, taking the output from the emitter. So this is going to be called common collector. And finally, you can show it to yourself that this last one is maybe called common base. So figure out why a common base name is applied to the last one. So these are the three stages. As I said, these are named according to the most simple configuration you may imagine. Just a transistor, and then you're looking at the input and outputs. We'll see that an actual common emitter stage is a little bit more complicated than that, or a common collector stage is a little bit more involved than just one single transistor. Just one single transistor obviously cannot do the job for you. You need at the very least some biasing, and then you need at the very least a resistor to convert the current through your control source to a voltage. So let's start with this stage. Common emitter stage is the most common amplifier stage. Well, and common source if you're talking about MOSFETs. The reason that it is the most common amplifier stage is that it gives you a good voltage gain, a good current gain, a large input resistance, but unfortunately a large output resistance. So that's, as a voltage amplifier, if you go back to the previous lecture, we said that if you have a voltage amplifier, ideally you want a very, very large input resistance, a very, very small output resistance, and some gain that is independent of everything else around it, right? So a common emitter amplifier gives you a good voltage gain, gives you a good input resistance, but the output resistance is not that good. And therefore you need other stages. There is a reason that we need those other stages. So let's look at a basic common emitter stage. The most basic common emitter stage is going to look like this. Okay, so this is as simple as it gets. We have a transistor that I bias it to be in active region using VBE, the source VBE, not between the base and ground. I just put just the right amount of voltage there to get the current that I need here to make sure that IC is in a certain value such that the base collector diode is off, the base emitter diode is on. And because the collector is a current source, what I do is that I put a resistor RC to convert that current into a voltage, because I'm looking at a voltage amplifier in this case. So this is as simple as it gets. The input is between base and emitter, as you can see. The output is between collector and emitter. It's the basic common emitter stage. So this is called the most simple common emitter stage that you can make. By this time, I'm hoping that you can see some flaws in a design that simple. But very soon we're going to talk about how we can address them in a second. Okay, so assuming that this device is properly biased, what I need to do next is to do the small signal analysis. So I go and draw the small signal model for the device. The device is biased and with some current IC, so let's just call it IC. For the transistor, I can use the small signal model, GMV pi, plus and minus B pi here, and this is R pi, of course. The base emitter and terminal, collector terminals are like this. IC goes in, IE comes out, IB goes in, right? This is an NPN. We saw for PNP, the model is exactly the same. Everything is exactly the same for the small signal model of a PNP device, right? Even the directions of currents are going to be the same. So this is my transistor. I draw the transistor first because usually, this is a 3-terminal device that has more connections, right? Now I go back and look at my circuit. This is a small signal model, so the DC values, the large signal sources are removed. If I look at the emitter side, emitter is directly connected to ground. Okay, so be it. That's easy. The base is connected to my small signal source. So here is VI or V in. And below V in I have the DC source VBE naught that for the small signal analysis it's replaced with the short circuit. It is zeroed, right? So therefore it doesn't show up in my small signal model. On the collector end I have an RC. At the top of RC I have VCC, which is a large signal source again. If I zero that, VCC is going to be shorted to ground. And because I'm drawing ground at the bottom of my circuit, I prefer to draw RC like this here as well. And this is V out. Okay. Now, if I look at this circuit, I can define R in as the resistance that I look from this node forward and R out from that node backwards. So that's on the large signal model. On the small signal model, R in is the resistance that I see when I look into the base. R out is the resistance that I see when I look back at the collector terminal. So it includes RC in there. Okay? So that's the circuit. That's the small signal circuit. And I want to analyze it. I want to figure out what is V out, V in relationship, what is R in, what is R out, all those things. So I look at this circuit and I say, okay, I want to find V out. Okay? If I look at V out, I can see that V out is the voltage drop across RC. So I look at the current through RC, I notice that the current through RC is just GMV pi, right? So GMV pi, there's just one current source, one resistor, and one end of the resistor is grounded. So the current is GMV pi, and the resistor value is RC. So that's V out. But what I notice is that the current is going from ground up. So the voltage drop across the resistor will be more positive on the ground side than the other side. So what that means is that I have to have a negative sign here. Okay, so V out is minus GMV pi RC. Okay, I look at that equation. I know GM from my DC analysis. RC is a component value. I don't know V pi. So I need to figure out the relationship between V pi and V in if I want to figure out the relationship between V out and V in. I look at this circuit. Well, this is lucky because if I look at this corner of the circuit, all of V in drops across R pi. Or in other words, I can see that V pi is equal to V in. And knowing that, I can show that V out is minus GMRC V in. Okay? If my intention is to find gain, I can figure out the gain value right away. AV, the ratio of the output to input, is minus GM RC. So I think this shouldn't be a new result for you, right? So we have analyzed this circuit before in different ways, and I think you have seen it before. Now, just to create a flashback here, recall that GM was IC over VT. So if you plug that in, this is going to be minus IC, this is the DC IC, RC over VT. And then we actually had the same result when we solved the circuit using the large signal model, right? But nonetheless, the point here is that I can calculate the gain relatively easily. I don't really have to worry about the large signal model anymore. And that task is done. Now, what about the input resistance? Well, we said that the procedure to calculate the input resistance is that you go and remove all the independent sources in your circuit, attach your test source to the input of the circuit where you want to measure the input resistance, and you measure the current that goes into the circuit. So if I want to do that here, I go and redraw the circuit. So it is And in this case, because I'm only measuring the input resistance, I really do not have an output. So this is the circuit, and I go and attach my test source. Let's call it Vx. And I measure Ix. The ratio of Vx to Ix will give me the input resistance. Well, again, lucky us, if you look at the Ix value here, Ix is Vx over R pi, right? Because the voltage drop across the resistor, R pi is V pi. V pi is equal to Vx. So very easily I can show that R in this case, just Vx over Ix. The ratio of these two is just R pi. Okay? So that was easy. Now, if I just spend a second between my calculations, I could have actually done the same thing. I know V in at the top. It was an ideal voltage source. I removed V in, I put another ideal voltage source in its place. And I don't have a value here. It is just basically just variables. I didn't really have to do that. I didn't have to add a Vx to measure Ix. I have calculations for at the top for the gain for V in. I could have used those calculations to calculate R in as well. As long as my V in, the input source, doesn't have a series resistance, for example, right? Because all I did for the second part is that I removed V in from the top part, put another V that essentially is the same in a small signal source in its place. I could have saved myself a little bit of time, but nonetheless, this is the procedure. So we followed the procedure. So R in is given, AV is given here, R in is given here. The next step is, or the final step is to figure out what R out is, and I need to go and redraw the circuit again. So again, I have my transistor here. RC here, GMV pi, plus and minus V pi here. And I always put the polarities of these important voltages like V pi on my drawings and draw the arrow in the current source to just keep myself, just remind myself that these are the directions, right? So this is the circuit. Now what I want to do here is that for output resistance, again, I remove all the independent sources. And in that case, V in is the independent source in that circuit. So by removing it, it means that I short circuit it to ground, right? It's a voltage source. If it wasn't current source, I would open circuit it. Then I go and look at where I need to measure the output resistance. I attach a test source there and look at the current that the circuit draws from that source. So this is where I attach my test source. Let's call this guy Vy. I need to measure Iy. The ratio of Vy and Iy will give me the output resistance of the circuit. So I need to solve this circuit. Now, again, a quick inspection here tells me something that makes my life easy. If I look at this circuit, you notice that V pi is 0, right? So you have 0 volts at the top of R pi, 0 volts at the bottom of R pi. Both are ground. So V pi is 0, meaning that GMV pi is 0. Okay? So if GMV pi is 0, then actually this current source, you can leave it as open. Now if I look at Iy is GMV pi, the current source, plus the current that goes through this resistor. So that one is Vy. I'm applying it to RC. All of that voltage drops across RC. I already figured that this part is 0, so Vy and Iy I can relate right here. So I can show that R out, which is Vy over Iy, is just RC. Okay, so done. If I want to take that amplifier stage out, that not complicated, but that transistor stage out, and just replace it with a voltage amplifier model that has an input resistance, output resistance, and gain. This is the values that I should use for that stage. Now, this was for a BJT. As I said, this is the most common amplifier stage. If you want to look at the current gain, what you should do is that you can actually go and short circuit the output to ground, right? So you short circuit the output to ground and you measure the current that is pushed to the output. So this is I out. And I'm going to leave it as an assignment to you. Then you look at the value of I out, the current that goes to ground, versus I in, the current that goes into the system. And calculate that, right? You can show that the current gain in that case, AI let's call it, is just going to be beta. Right? Think about it. It's the collector current over the base current. Right? If you short circuit that RC out, if you short circuit the output to ground, it's the collector current to the base current. So it must be beta. If you go through the small signal analysis, you actually will see you'll arrive at this expression. So it is GM R pi. But remember that R pi is beta over GM, right? So once you simplify that, it is beta, which is what we expected from the large signal behavior of the device anyway. So you can have a current gain of beta, and we know beta is large. You can have a voltage gain of GMRC with a negative sign, of course, but magnitude-wise, you know, it's just easily can be tens or even hundreds. The input resistance is R pi. So if you do a few calculations, you see that normally for milliamp type of currents, it's on the order of kiloohms. It's not too large, but it's not small either. But the challenge is that output resistance RC is usually large. Why is it usually large? Because I want a large gain. So IC-RC that I use for AV, I have some level of IC, let's say 1 milliamp, and RC is 10 kilo ohms so that I can get a 10 volt voltage drop across RC. And that 10 volt voltage drop will give me a gain of 400, right? So I use a 10 kilo ohm resistor to get a lot of gain, but at the same time that large resistor that I use for large gain is going to increase my output resistance. This is a deviation from a good voltage amplifier. I want a good voltage amplifier to have a small output resistance. In this case, I have a large output resistance. So, now, if you look at this circuit, just by looking at it, I don't think, you know, most of you shouldn't really like it that much. The problem with that circuit is that I'm putting a fixed voltage across the base emitter junction. And we know that's a bad idea because as soon as the temperature in the environment changes a tiny bit, you know that VT changes, you know that VBE on changes, and therefore you're going to get a hugely different current. Remember from the diode section that for every 60 millivolt of change across a diode voltage, you get a factor of 10 difference in the current. Well, you have designed this to be at a stable bias point. The current really shouldn't change by more than a few percentage points from its designed value. And then, you know, if you have a few degrees of change in temperature, then you can have a few millivolts of change in VBE on, and then that can have a factor of 2 or 3 change in collector current. Most likely what will happen is that your device will enter saturation or cutoff because of those changes. We don't want that, right? So one solution is to go and add a resistor to the emitter terminal. So instead of having the emitter directly connected to ground, I have a resistor there. I still take the output from the collector, But now I have a resistor in the emitter terminal. We're going to talk about the biasing very soon, in the next lecture. But this resistor in the emitter circuit will absorb those changes of VBE, will control the behavior of the circuit by a great deal. So for example, if you want to go back to the diode section and diode discussion, let's look at this simple circuit. If I have a diode that is directly connected to VCC, and you're looking at ID and this is VD, the tiniest change in VCC is going to create a huge change in ID because all of that VCC has dropped across the diode. By putting a resistor here, now this resistor is acting as a moderator. So some change in VCC is still going to cause a little bit of change in the diode current, but the change in the diode current will also change the voltage drop across RD. And that RD doesn't allow too much change in the diode current. Right? It moderates it. It basically keeps it in charge. Same thing happens here. So just accept that for now. We're going to talk about the biasing in more detail. But it is very, very common to have a resistor in the emitter circuit for this device. So this resistor is called emitter degeneration. And we'll see that it has some biasing advantages. Also, from a small signal point of view, it changes the behavior of the circuit that needs to basically requires a new analysis here. So I'm going to do the analysis. I'm going to look at input resistance when I look into the base, output resistance when I look back into the collector, and then obviously the voltage gain, which is the output voltage amplitude to the input. Let's draw the small signal model. So I draw the transistor again first. Attach the circuit components to it, so RC between collector and VCC that is now grounded. Emitter now has a resistor in it. My source GM Vpi, this is Vpi, Rpi value, and at the input I've removed the DC source and only have V in left. This is V out, and if I want to draw or be explicit about R in, R out values, this is where I measured. Okay? So this is the new circuit to analyze. Looks like the previous one. The only difference is that RE has removed emitter from ground, right? So now there is a little bit of a connection between the base and emitter. In the previous circuit, with emitter being grounded, your input circuit was entirely separated from your output circuit. Anything that happened at the output really didn't do anything at the input, or things at the input simply changed the Rpi value, Vpi value, and then there was no connection, no other connection beyond that between the input and output. Now with the inclusion of RE in the circuit, I have some connection between input and output of this circuit. So let's go and solve the gain problem first. So I look at V out. I want to find V out, V in relationship, right? So I look at V out. Like before, V out is still given by the voltage drop across RC. I look at the current through RC. It is still GM Vpi. There is no other node here. So V out is minus GM Vpi RC. Okay? So this is the same as before. My output circuit hasn't changed. But the problem is that Vpi in this case is not V in. If I look at the input circuit, Vpi is a portion, is a fraction of the voltage drop from base to ground. Okay? So now I need to write a KVL there. I can see that V in is equal to this Vpi, right, the voltage drop here, plus VE, plus this voltage. The voltage drop across RE. Now, how much is that voltage drop? Well, it is a resistor, so I look at the current through it. The current through RE is made of these two currents, the current that comes from the base side and the current that comes from the collector side. So it is V pi plus the current from the base side is V pi over R pi, right? So this is the resistor that I have R pi. The voltage drop across it is V pi. So the current that goes through this resistor is just V pi over R pi. The current from the collector side is GM V pi. Now if I look at this equation, I have a relationship between V in and V pi. The equation at the top gives me a relationship between V out and V pi. I can eliminate V pi and have a relationship between V in and V out. So let me just okay. Now, again, those of you who have done a few circuits already, you should obviously see here that when I'm adding GM to R pi, well, what are the values? So R pi is beta over GM. So 1 over R pi is GM over beta, right? So 1 over R pi is GM over beta. I'm adding GM to GM over beta. In most cases, in most situations, beta is large, so GM over beta is much, much smaller than GM. And if you ignore the first term here, you're not really going to create a lot of error, okay? Now one point that we missed here is that this has to be multiplied by RE, right? So this is the current times the resistor. So there is an RE here as well, okay? So if I assume that beta is much larger than 1, then I have these two equations. So at the top I have V out is minus GM RC V pi, and from the bottom I have V pi is equal to, I'm going to rewrite that equation, V in over 1 plus GM RE, right? If you replace this with GM, the entire thing becomes GMRE. If beta is much larger than 1, which is usually the case, even for a beta of 25 or 30, that's still a good approximation. And then if I have that, then I can actually plug V pi from the bottom equation in the top one, and therefore I have V out as a function of V in. It's going to be minus GMRC over 1 plus GMRE times V in, or your gain value is minus GMRC over 1 plus GMRE. Okay. Right away I can see that by including that RE in the circuit, I have lost some gain, right? Because GMRE is a value that is larger than 0, and originally my gain was GMRC, now it is GMRC divided by some number that is larger than 1. So it's definitely less than the original common emitter circuit. However, this is the price that you need to pay for all those stability benefits that we mentioned earlier, bias stability and things like that. So you traded off gain for some bias stability, okay? This is a very common trade in electronic circuit design. You usually trade gain for bandwidth, gain for noise, gain for input resistance. Gain is the currency in amplifier design, right? So you design a high gain amplifier, and then if you see that you're not meeting some performance aspects, usually you trade some of that gain and improve the performance parameter that you're interested in. Now, okay, so let's calculate the input resistance. I usually do these two right after the other, the input resistance and gain calculations, because as we mentioned before, as long as your source is an ideal source and doesn't have a source resistance, the calculations are the same. I'm still attaching a test source to the input of the circuit and looking at the current from it. If I'm doing the calculation for a input resistance, I can reuse some of the calculations I did for voltage gain if the voltage source in that case was ideal. So if I calculate I in here, I can calculate the input resistance right away. So what I do is that I look at the circuit, I notice that I in this circuit, it's just V pi over R pi. Okay? So I in is equal to V pi over R pi. And I've already done the analysis, used this equation that I have from before. So it is V in over R pi times 1 plus GM RE. Okay, so I already have a relationship between V in and I in. If you would like, just go and attach a test source Vx to your input and calculate Ix. I'm making my life a little bit easier. I'm careful about it, but from time to time you can do this. So therefore R in, which is the ratio of the input voltage to the input current, is going to be R pi times 1 plus GM RE. And now this is an interesting result, right? So I can see from the expression for AV that my gain has dropped by a factor of 1 plus GM RE. But by looking at the expression for R in, I can see that my input resistance has increased by a factor of 1 plus GM RE. The original common emitter stage had an input resistance of just R pi, right? Now it is R pi times 1 plus GM RE. It is that many times larger. But that's something good. I sacrificed gain, which is something that I want in a voltage amplifier. I sacrificed a little bit of it, but I received an improvement in input resistance, which is something I like. A higher input resistance is something I like in a voltage amplifier. So that RE, it reduced my gain, but it increases my input resistance significantly. And we'll go through an example and show you some numbers of how much we're talking about here. So that's good. Then last part is to calculate the output resistance. So I go back, redraw the circuit, attach my test source to the output, and this is what it is going to look like. So I have my transistor here, RC here, RE here, V pi and R pi and GM V pi here. Now the input source is grounded, removed. I attach my test source to the output and want to measure that IY. Right away I see that IY is going to divide between these two currents, the current that goes through RC and the current that goes to the collector. So I can see that IY is VY over RC, so that's this current, plus GM V pi. Okay, so I know VY over RC, that part is easy. I have to worry about V pi. I need to figure out what is the relationship between V pi and VY, because I want to just have an expression in terms of VY and IY. So I look at the input circuit. I can write a KVL from here to ground. So 0 is equal to V pi plus VRE. And again, we can say that VRE is this current plus this current times RE. So this is V pi plus current from the base side is V pi over R pi. Current from the collector side is GMV pi times RE, and that's 0. Okay? Now, I can see that V pi times 1 plus RE times 1 over R pi plus GM is 0. So what does that mean? Well, this term is non-zero, right? At the very least it is 1. So something times V pi is 0, from here you can see right away that V pi is 0. Okay? What does that mean? Why is V pi 0? I have connected the source to the output. Why is V pi not a function of that, or is not responding to that? Well, this is the reason. You have applied a voltage source above a current source. Whatever changes voltage in voltage that you have here, the current source doesn't care. The current source can take any voltage across it. So all the changes of the voltage here will not affect the current through the current source here. The current source here is a function of something else in your circuit. So basically, you have separated V out from the input side of your circuit by having a current source in between them. But what that means is that it turns out that the current source is also 0 because V pi is 0. So if you take that equation and bring it here, then you can see that R out, which is Vy over Iy at the end of the story, is RC. Right? So we didn't have any change at the output end. Output resistance is still RC, but my input resistance has gone up, my gain has dropped down, both of them by the same factor, 1 plus GMRE. Now let's go through one example here to see some numbers, to put some numbers to these equations and then have a relatively realistic expectation or numbers for the